Swayam Prabha. Digital India. Educated India.
This Maritime Engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar.
So in the design of reinforced concrete structures against fire, we have seen how thermal calculations are done, what are the assumptions and idealizations behind thermal analysis and structural analysis, and we have also seen 500 isotherm method with examples, how that can be used for idealizations with respect to concrete, as well as we have seen design of beams in detail and how this 500 isotherm method can be used for design of beams. Okay. So just to quickly review what this 500 isotherm assumption is, it simply states that concrete within the 500 degree isotherm remains unaffected, which means it has full strength. Okay. So if this red line shows the 500 isotherm, concrete inside this has full strength FCK. So this is case of beam, this case of column with all four sides exposed. Okay. Concrete outside of this has zero strength, which means we need not consider it. Okay. For the rebars, we actually compute the temperature and consider the strength reduction factor appropriately and take those into design calculations. This is the basic of 500 isotherm method. We also saw that in case of slabs which are generally exposed on one side, so slabs generally exposed on one side, here we have beam which is three sides, column, this is four-sided exposure, although columns can also be three-side exposed, one side or two-side exposed depending on the condition. Okay. Now for slabs, the 500 isotherm will be a straight line which is parallel to its surface. Okay. And this is what say x 500 will be if you are using x coordinate in that direction, where here we were defining x 500 and y 500. Okay. We already defined these things and we also saw how to calculate this. So in case of slab, much of the concrete which is under compression will remain functioning because the neutral axis say lies somewhere here, and anyway concrete below the neutral axis which is in the tension zone, that is anyway not considered for design. Okay, so this is the basic overview of the 500 isotherm method. Now the next kind of structural member in RCC will be slabs. So we look at design of slabs. Now it is customary or usual to consider design of slabs as similar to design of beams, except that for B we give B equal to 1. However, one major difference happens in the thermal analysis. So let us say we have this slab, okay, which has a reinforcement going there, like this, and slab will be say generally supported on maybe masonry wall, or it may be supported on a column like that. Okay, the fire scenario will be such that if there is a room at the bottom where the slab is covering it, the fire happens inside the room. Okay, so only the bottom surface receives this heat, and hence this is a 1D heat transfer problem instead of 2D. Okay, so in case of columns or beams, okay, in case of columns or beams, we can have one-sided exposure, two-sided exposure, three-sided exposure, or four-sided exposure. Okay, these are the possibilities. Whereas in case of a slab, we generally have only one-sided exposure. Because the exposure is one-sided, we can do thermal analysis also in one dimension instead of in two dimensions, right? And we have seen this when we were doing the Wickstrom method. We just oriented this in a vertical manner, which means for the purpose of orientation, when we are doing Wickstrom method, we said it is like this, where this is the x axis, okay, exposure is on this side, and then temperature distribution on this x axis will be like this for an insulating material, where Ts is the surface temperature which links with the fire temperature through convection and radiation, right? And then if you recall, we also defined this delta. Okay, delta was the penetration depth. So we can talk about say delta 500, which is depth at which temperature is 500. Okay. So thermal analysis can be done in one dimension, which is a great simplification. And in fact, you may find it a bit ironic also that from a structural behavior point of view, slab is a 2D member, okay, a plate-like member, but from a thermal analysis point of view, it becomes 1D. Whereas columns or beams, from a structural analysis point of view, these are 1D members because one length is much long compared to the cross section. But from a thermal analysis point of view, these are 2D members. Okay, this is a bit ironic, but that is how it is. And the reason for that is clear from this, the overall exposure conditions. So let us look at an example. Okay. In fact, before we go to the example, one more thing I would like to point out, which is that for slabs, it is usually that we take a 1 meter strip, say B is equal to 1 meter. Okay, we take 1 meter strip and that is what is designed. Okay. So either this way or that way, in both directions. Now because of the nature of our exposure, okay, this B will not change with temperature. Okay. So for beams or columns, this B became B fire, which was B minus 2 times X500. Okay, this capital D became, sorry, small d became small d fire, where it was capital D minus A fire, right? A fire was the location of centroid as temperature changes, centroid of the tension rebars. However, in this case, since it is one-sided exposure, there is no reason why temperature here and here will increase independently of here. So the B remains the same. So there is no B fire as far as beams are concerned. Okay, so now let us look at this example. Okay, there is a simply supported slab of span this much, thickness 200 mm. So this is capital D. M30 grade concrete, FCK is M30, 16 mm diameter, 415 bars. Okay, the spacing is given. Clear cover is 15 millimeters, and the bending moment demand per meter is 70 kilonewton meter. So now we have to determine its fire rating or fire resistance subjected to a standard fire from the bottom. Okay, so let's now begin to consider this directly in the code. Right? So in the given data, we have B and D. So B we have taken as 1 meter. Capital D is 200 millimeter. CK M30, so 30 megapascals. 415 steel, so that is this, and this is the spacing. Okay, so the spacing in this case will be required to calculate area of steel. In case of beams, we get area of steel simply by saying area of one bar multiplied by all the bars which are there, right? Okay, this is the diameter of the bar, 16 millimeters. This is the clear cover, which is also given. Okay, so C bar, this is like A. The C bar is centroid of the rebars. This is like A, which we are calling C bar in case of slabs. Okay, so this is C bar, which is clear cover plus diameter of the bar by 2. Okay, centroid of the bar from the bottom. AS, which is area of steel, it is width, which is 1 meter, divided by spacing, multiplied by area of the bar. Okay, this is the total area of steel AS. Then M demand is the total moment demand. Now, since we will be doing a one-dimensional heat transfer problem, okay, we are doing thermal analysis of the 1 meter strip. Bottom surface is at x equal to 0. Okay, so if we have slab located like this, the coordinate axis is oriented this way. So this is x. Okay, and this point, bottommost point, is x equal to 0. Okay, and the centroid plane of the bars is at C bar, which is this. Tf is fire temperature, standard ISO 834. Okay, then we use Wickstrom method, so Ns, Nx, and we calculate Tx. Okay, so Tx is temperature of each such point as a function of time. Now in this case, Tx is a matrix where each column represents one time step and each row represents one coordinate in x. Once we have done the thermal calculations, we move on to structural calculations. Okay, so we get for Tx, which is for the centroid location, we get the strength reduction factor for the rebars. Okay, now force taken by the rebar, which is force in tension, is Ksy, which is this factor, multiplied by Fsd, cold strength, multiplied by As. Okay, force taken by concrete. Okay, now lambda is 0.8, eta is 1 because Fck is less than 50. Okay, so again using the same rectangular stress block, we are calculating depth of neutral axis. Once we have depth of neutral axis, we are calculating moment capacity. Okay, moment capacity is like this. Now inside here, this is what is Z or the lever arm. So d minus c bar, this is small d, this is lambda x by 2. Okay, so this d minus lambda x by 2, this is z, this is the lever arm. Once we have done these calculations for all times, we can find out moment capacity as a function of time. Okay. So initially it starts here, then it reduces, and using this we can find out the fire rating. Okay, so fire rating or fire resistance in this case comes out to be 1 hour or 60 minutes. Let us look at one more example. Okay. So again, a simply supported slab, 4-meter span. Okay, span is lesser, depth is same, 200 millimeters, M25 grade concrete, 18 mm diameter, 415 bars, spacing is 125 mm. Okay, and clear cover is also same. We go right into the code. We have geometrical parameters B and D, FCK, Fy, spacing, diameter of the bar, clear cover. Okay, this C bar is like the small a earlier, which is clear cover plus diameter of the bar divided by 2. Area of steel will be B by SV times area of 1 bar. Okay, so B by SV is 1 bar. How many bars we have in that spacing? Moment demand is 50 kilonewton meter. Then we go on to thermal analysis. For thermal analysis, we are calculating it up to 4 hours. Okay, XS is the coordinate of the centroid plane of the rebars, X coordinate. TF is temperature of the fire. Okay, again ISO standard 834 curve. And this is the for loop for temperature calculation using Wickstrom's method. We've been using the same method throughout for RCC. So we have now this structural temperatures, right? So this Tx has been calculated. We have Tx. Now we can take the rebar temperatures out. Okay. After we have taken the rebar temperatures, we calculate the strength reduction factor for rebars. Then we calculate forces taken by the rebars. Okay. Similar type of calculations. So the code does not change. Only thing that changes is the initial inputs, okay, of the geometry and of the rebar and strength and other things. So again we calculate moment capacity and we can plot it with respect to temperature or time. Okay, temperature and time are correlated through the ISO 834 curve, and the fire rating we get here is little over 1.5 hours. One thing we will notice here is in the cold condition there is a larger difference here between the demand and the capacity. Okay, whereas in the previous example this difference was small. Okay, so this is one of the things which is very common, and it is obvious also that if you have more spare capacity, okay, you may recall in one of the lectures we were saying that there is a design effect and there is a demand resistance. Okay, during fire what happens is that this you know uh, like that, so the margin of safety reduces. That is what we were saying. Okay, so if initially we have a greater margin of safety, it will take longer for this thing to fail, and that is what is visible here, that we have a greater margin of safety here. Okay, and the fire rating is greater. Okay, this is quite common, and several codes understand and accumulate the fact that if the loading ratio, okay, so this is defined as the loading ratio in steel. IS 800 also does that. Okay, so the loading ratio was defined as the demand divided by the capacity, right? So if the loading ratio is small, the fire resistance rating is expected to be large. Now let us look at table 16A. We were looking at it when we were doing the examples of beams. Now we look at this particular column which is on slabs. Okay, so for simply supported slab, these are the minimum cover requirements for particular type of fire rating. Now again in our case, the clear cover was 15 millimeters, so it is not part of any table. So either we don't use it and we have to go to specialist literature or calculations, which is what we have done, or it is also possible to conclude that if 20 mm cover is required for half an hour 30-minute fire rating, for a 15 mm cover the fire rating will be less than half an hour. Okay, but that we know now is a conclusion which is incorrect. Okay, so the clear cover is 15 mm. This is the first beam where we had the fire rating of 1 hour. Okay, whereas obviously from here you cannot conclude. Okay. Now here we are referencing only table 16A. We are not referencing that figure 1 of IS 456 because figure 1 does not have anything related to slabs. Okay, so this is the first example. Second example also, clear cover was 15 but fire rating was higher. Okay, so simply the effect of this loading ratio cannot be taken in tables of this kind, and this is where detailed calculations are necessary for us to be able to actually calculate the requirements. Now let us move on to study design of columns, RCC columns. Now this particular thing shows again 500 isotherm. We will use the same method. This fully closed 500 isotherm is a case when a four-sided exposure has happened. Okay. But we know that if there are other sites of exposure, then this 500 isotherm will be accordingly adjusted. Right. So for we know that if the column is taking axial load, okay, there are two parts. One is the compression taken by concrete, one is the compression taken by steel. Okay, so for concrete we will have area of concrete which is B fire times D fire, or in this case H fire as in the diagram. Right, so that is the effective area. This is the area of concrete that is effective at any temperature, which is inside the 500 isotherm times FCQ. So this is strength of concrete in compression. and then there will be NS fire, which is the load taken by rebars. So for rebars, we will take each rebar and factor in the strength reduction factor. Okay, so that will be this, and total will be a combination. In fact, there is an error. This should not be divided by the area, otherwise it becomes the total stress. So we are looking for total force here, so that is only this numerator. Okay, and as we had been saying, if we have other exposure conditions, okay, let's look at some of them. If we have, say, two-sided exposure, which is here and here, then the contours will look like this. Okay. So this is how the 500 isotherms will be. If you have two-sided exposure from opposite sides, okay, then your contours are looking like this. So depending on the exposure, these contours will have different shapes. However, the overall calculation methodology would not change. We will still require this 500 isotherm. Okay, so in this case, if this is the 500 isotherm, here say these two are the 500 isotherm. Okay, so concrete inside is to be considered, concrete outside is to be ignored, and for rebar, always we will calculate actual temperatures and actual strength. So this is the case when we have pure compression. However, there can be combined loading conditions where there will be a moment as well as a load. In such a case, we will have to do section analysis in line with these assumptions of 500 isotherm, and we will have to develop this PM interaction. Okay. And what one can expect is that if, say, this is the PM interaction in cold conditions, okay, under fire conditions, this interaction will, the diagram will shrink. So increasing temperature, so temperature increases this way, so the diagram shrinks. Okay. However, the calculation approach will be same. There is no change. Let us look at an example. So we have a short reinforced concrete column of dimensions 500 by 400. Grade of concrete used is M50. Okay. Fe 500 grade steel is used. Diameter is 20 mm for all the bars. Okay. And load demand is 8000 kilonewton. So this is what we are showing here. I think there is one change in the text here. So these intermediate bars, internal bars, these are 20 mm, but the external bars are 25 mm. That is a difference. Now we follow the coding approach that we have been doing. Initially we have B and D. So B is for, so here we are calling B as 500 and D as 400. Okay. FCK is 50 MPa. We are using Fe 500 steel, so FSD is that. Okay, both. The demand load is 8000 kilonewtons. Okay, so just like we did for beams, we do a rebar data structure for all the rebars. Okay, now here this is a four-sided exposure, so we have fire on all four sides. So from a temperature contour point, they will be circular in nature. So we will see that this four bars, okay, these will have the same temperature, and hence they are labeled all of them as 1, whereas these also will have same temperature and they are labeled as 2. Okay, so this first row corresponds to the first rebar here. So the x and y coordinate is 50-50, diameter is 20. Then this is second, where x coordinate is 183, okay, where is 133 plus 50, y coordinate remains 50, diameter is 20, so these two bars are of 20 mm. So like this, and similarly this last one is here, okay. So this is how we have defined the rebar coordinates and their diameter. Now for thermal analysis, we will have to again go back to two-dimensional analysis. Okay, for slabs we were able to use one-dimensional analysis. So we are doing modeling up to 4 hours. X and Y coordinates are like this. Now here, since it is a 4-hour exposure on all 4 sides, okay, we can see that the axis of symmetry lies on both sides, which means we can take only 1/4 and we model only this because we have axis of symmetry. So this axis of symmetry is happening, two axes of symmetry, because we have 4-sided exposure, and also the geometry and the rebars are equally distributed about these two axes. So for x's and y's, we are only modeling up to b by 2 and d by 2. Then this ND grid is same as that we were doing earlier for enabling us to calculate contour of temperatures in 2D. Okay. TF, same as earlier, fire temperature corresponding to ISO 834 curve. Okay. Now this loop calculates temperature. The third index T denotes time, so which means we are storing one matrix for each time, and each matrix corresponds to the XY coordinate temperature within this symmetry section. Okay. Now using this one can plot. Okay, so we will get the temperature contours. Now one thing we should not get confused about is when we plot these temperature contours, they will look like this. So we should not take this to be a two-sided exposure, because we know that now we are modeling this part only. Okay, so in reality we have to then replicate it on all 4 sides with symmetry. So eventually they will become close contours as we had been seeing earlier. But because we want to save time on thermal analysis, we have only modeled 1/4 of the section. Okay, so if we plot contours here, this is how they will look like, but the interpretation will be like so. Okay, so once temperature calculations are done, we move on to structural calculations, right? So first thing is we find out the X500 and Y500. In one of the lectures, we saw this function locate X500 and we saw how it works. Okay, so this XX500 is coming out of this contour function, which is a 2 by n array, where after the first column, each column gives us X and Y coordinate of a point, of every point which is located on the 500 isotherm. Okay, so then we calculate B fire and D fire. In this case, we will require both because the overall cross section is reducing. So B fire is B minus 2 times X500 and D fire is D minus 2 times Y500. This is B fire, okay, which is B minus X500, and this is D fire, which is capital D minus Y500, where Y500 is this distance, X500 is this distance. So now that we have completed the thermal calculations and also we have found the location of the X500 and Y500, okay, so subsequently we have calculated B fire and D fire. Now we can move on to structural calculations. So before we can do structural calculations, we also require rebar temperatures. Okay. So this we obtain in a manner similar to what we did for beams. So rebar, each column of this data structure, first two columns give us the x and y coordinates, third column gives us the diameter. So we calculate x, y. Now if x coordinate is more than b by 2, which means if x coordinate is here, then we have to bring it back to here. Okay. If it is here, we bring it back to here. This is because we have modeled symmetry about this axis. Okay, so that is what is done here. So if it is more than b by 2, we say it is b minus b bar. So this bar and this bar will have same temperature. In this case, because it is a four-sided exposure, we have also used symmetry about this line. Okay, so if y coordinate is greater than d by 2, which means if y coordinate is here, we need to map it to this particular thing, right? If y coordinate is here, we need to map it here. So that is what is being done in these two lines. So once we finish this, then we have the x coordinates and y coordinates of the rebar. Then we calculate the temperature at that xy coordinate using this Wickstrom's method. Okay, so this Ts rebar, this is Ti, temperature of each rebar we get from here, and then this is Ki, reduction factor for each rebar. Okay, and this last one is Ai, which is area of each rebar. We have calculated all of that. Then we can move on with structural calculations. Okay. So here we are calculating first the average stress taken, compressive stress taken by all the rebars. Okay, which is the summation of K times FSD times A. Okay, so summation of KI FSD I AI divided by summation of AI. Okay, so this is FSD average, or in a fire condition, that is this. Okay, now we take this and multiply with the total area of steel. Okay, that gives us the NS fire. In a previous slide where we saw this NS, we can also simply write this as the summation of the numerator here. Okay, we can also write this as KI FSD I AI. So this is also the total compressive force taken by all the rebars combined. Now this NC fire is the compression force taken by the concrete. Okay, that is simply B fire times D fire, which is the cross section area, multiplied by FCK. Now obviously FCK, there is no reduction, and the reason there is no reduction is that is what 500 isotherm method assumes, that within 500 isotherm there is no reduction in concrete strength. So we have these two, then we can calculate the total capacity, which is capacity due to concrete, capacity due to steel, and we divide by 1000 to ensure that the units are in kilonewtons. Okay, because our demand we have written in kilonewtons. So once we have all of this, we can plot. On y-axis is axial load capacity, x-axis is time, and as always, since we are using ISO 834 curve, time is directly proportional to temperature of the standard curve. And what we can see from here is that fire rating is just a little bit less than 2 hours. Okay, and fire rating is when this capacity crosses the demand, right? So demand is being shown here. Demand was 8000 kilonewtons. Let us look at one more example. Okay. Now again, we are looking at a short reinforced column. Dimension is 450 by 450 mm. Grade of concrete is M40. Grade of steel is Fe500. Okay, and diameter of bar is 20 mm. Centroids located 40 mm from the edges of the column. Okay, load demand is 5000 kilonewtons. Okay. So we can draw this. We have 500, sorry, 450 by 450. It has 4 bars, which means they will be located at one at each corner. Each bar is 20 mm, 5. Okay, and the centroid distance, this is 40 mm. This is also 40 mm for all of them. Okay. So we can begin in the code. We'll say now B and D both are 450 millimeters. We are writing it in meters, so this 10 power minus 3 is there. Concrete strength is 40, steel strength is 500. Okay, demand load is 5000, and then now this is the rebar data structure where this is coordinate, x coordinate of all the rebars, y coordinate of all the rebars, and this is the diameter. Okay, so we'll see that for the first bar coordinate will be 40 and 40. For the second bar it will be 450 minus 40, which is x coordinate will be 410, y coordinate will be 40. Okay, so that is what we have here, 40 40, then 410 and 40, then 40 and 410, this corresponds to this bar. So x coordinate is 40 but y coordinate is 410, and then this is the top right bar where it is 410, 410 and 20. Okay, this is the rebar data structure. Now we proceed with the thermal analysis of this thing, this column. We model up to 4 hours and we do a 2D analysis because this is a 4-side exposure. In thermal analysis, we are again using Wickstrom's method. We calculate Nx, Ny, Ns, temperature Tx. This is a data structure which directly can go in the contour function if you want to calculate the contours. And since we are again simulating only quarters of the column, which is quarter symmetry, it will be like that. The contours will be like that, and the interpretation has to come from us that it is using a quarter symmetry. Hence, we will reflect it this way, that way to get the overall close contours that we are expecting. Once we have the contours, we move on to structural calculations. Okay. So for structural calculations, again we first have to find the 500 isotherm. Okay. Once we have the 500 isotherm, then we calculate the x and y values. Right. So we have the x and y values. Then we calculate B fire and D fire. This is the reduced cross section or reduced effective cross section which is within the 500 isotherm. Okay. Then we calculate rebar temperatures. Okay. For rebar temperatures, we have this x and y coordinate, which are the first 2 columns of the rebar data structure. Since we are using symmetries in x and y both, okay, if it is more than b by 2, we reflect it back. If it is more than d by 2 on top, we reflect it back. So we get x and y coordinate of the rebars. From there, nx and y is calculated. Then we get temperature of rebars. Okay, so this is Ti, temperature. This is the factor, reduction factor, Ki, and this is the area of each rebar, Ai. Okay, so then again we can calculate this NS fire, which is for steel. Okay, that will be simply summation of Ki FSDI times Ai. So either this, or we can do it using the stress that is done here. And NC is simply B fire times D fire times FCK. Okay. Now the capacity total will be concrete capacity plus steel capacity. We divide by 1000 to make sure units are in kilonewtons. And then we can plot the capacity versus time. Okay. So this is the capacity versus time curve. So in this case, we will see that this initial loading ratio is very small, which means the actual capacity is much higher compared to the demand. Okay. So the fire rating that comes out here is almost 3 hours, okay, which is much larger compared to the previous example. So let's look at provisions of IS 456 again. So this is figure 1. Okay, so figure 1 we looked at from beam perspective also. This one has the figure 1 portion which is relevant for columns. Okay, so again on this axis, on this column we have the fire resistance in hours. Okay, then this gives the minimum dimension of the column which is required to achieve this kind of fire rating, and it considers three types of fire exposures. One is fully exposed, which is the two examples we have done, then 50% exposed. Okay, so it does say 50% exposed. However, whether it is adjacent sides or opposite sides, that is not clear. Then we have one face exposed. Okay, so from figure 1, let's say if we require 1 hour fire rating for under a fully exposed condition, minimum dimension required is 200 millimeters. Okay, that is how we can read this. Now table 16A has specifications for column also, clear cover. Okay, so in this case you will notice that all the clear covers required are 40 mm. Okay, so one of the things is that 40 millimeter sometimes is required from other requirement conditions also, such as exposure conditions. But one way to interpret this table can also be that minimum required for 4 hours is 40 mm, and minimum required for half an hour is also 40 mm, which is a little bit not easy to follow. So let us compare these two examples with the tables of IS 456. Okay, so in one of the examples we had B is equal to 400, D is equal to 500, and cover was 37.5. Okay, and in this case the fire rating that we found was a little bit less than 2 hours. Okay, maybe 1.9, 1.8 hours. Now if we go with, say, minimum dimension being 400, okay, for fully exposed conditions, one is this. One can say that expected fire rating will be 3 hours, whereas it is much less. Okay, and from this table, the clear cover of 37.5 is not available. Okay, but it doesn't mean that because it is less, then because even for half an hour you need 40 mm, 37.5 will have less than half an hour. That cannot be interpreted, right? So it is better to do this type of calculations whenever these fire ratings are required. Let's look at the other example where the fire rating was a little less than 3 hours or almost 3 hours. Okay, in this case B and D were same, which is 450, cover was 30 mm. Okay. So again, if we go to figure A, for 450 mm minimum dimension, one can say that expected fire rating is 4 hours, whereas it is less than 3 hours. Okay. And again, for this particular thing, which is table 16A, less than 40 mm cover is not available. So one cannot really interpret. So if we summarize what we have done in this lecture, we have looked at design of slabs and RCC columns using the 500 isotherm method. Okay, we looked at the thermal assumptions, thermal analysis assumptions. We looked at the structural analysis assumptions, and we saw how all of this can be used to calculate fire ratings using the 500 isotherm method. Are there more accurate methods possible? Yes, they are possible, but obviously they become more complicated in analysis also. And for many practical problems, even codes include these methods, for example, Euro codes. So these are practical methods of design which anyone can adopt. So for this method also, we have developed computer codes, which once you write one time, all we have to do later is just to change the initial parameters and be able to find the design requirements, or in fact the capacity versus time curves. And this capacity versus time curves is what we can eventually use to assess or estimate the fire rating. We also looked at IS 456 provisions for slabs and columns in this lecture and other members in the previous lecture for fire resistant design. And we saw that in most cases, most practical cases, it is a little challenging to use these 456 provisions, primarily because either the data is not available in the table, or it does not take into account a large number of factors. Okay, what are these factors? The loading ratio. Okay, loading ratio is not taken into account. The reinforcement ratio, the percentage of steel will have a role to play in fire resistance. Okay, but that is not taken into account. Grade of concrete, degradation of concrete strength. There are so many factors which, when we consider, we are able to get a more accurate estimate of fire rating of RCC members, and one of those methods we have learnt.